Hello everyone and welcome to the next session of our Digital Days. My name is Markus Eberle and I will moderate this webinar today, and I'm also very pleased to welcome Stephan Bächle today, who is our speaker, and he will hold the presentation and also after the webinar just answer your questions. He's working as a field application engineer at Würth Elektronik. So then we are also very happy that you took the time to participate in this webinar with the topic RedCube high power terminals. So just a few information from my side. You are muted in this webinar. This means that you have to tell us your questions all with the Q&A function. You will find this in the WebEx control panel on the lower right-hand side. There is a little question mark button, and there you can just send us all your questions, maybe send it to all panelists, then we have it all good here. So if we can't answer now all your questions within this live webinar, we will, or Stephan will later answer all your questions via email. And if you have any questions left after the webinar, just email us at digital-v-days@we-online.com. You will also get the link to the presentation as well as to the recording of this session in the next few days from us by mail. So then I'm happy to give it over to you, Stephan, and I wish you an exciting webinar.
Thank you very much, Markus. Hello together. Welcome everyone to our webinar in our Digital Days. My name is Stephan. I work as a field application engineer at Würth Elektronik since 12 years now. And I'm responsible field application engineer for the electromechanical range of products. The electromechanical range are connectors, switches, but also mounting materials. Today we speak about RedCube high power terminal. This is always important when it comes to high currents on your PCB. You need a proper connector to fit to this power, and therefore we have our RedCube series, and this is what I wanted to present you today. So when we are talking about power and connectors for PCBs, most of the connectors we find on our PCBs are more related to signals than to power. They are small connectors and they are suitable for 0.5 or only 1 ampere, like pin and socket headers, for example, or those small signal connectors. But there are also some connectors available up to 5 amps, 10 amps. And when we look to terminal blocks, we reach a region about 50 or 100 amps. But what is above? When you have to deal with more than 50 amps, it is really tricky to find a proper connector for this solution. Therefore, we have something special in our portfolio, the RedCube range. The RedCube range contains 3 different technologies. First of all, the press fit technology, the most reliable technology, suitable for the highest currents up to 300 amps over the PCB and up to 500 amps over a copper bar. And this is what I want to highlight today in this presentation. But we also have some other power connectors like our RedCube THR. I will show you them at the end. If you are not able to do a press fit, you can also have solder connection with the RedCube THR, but be aware those connectors are only going up to around 85 amps and the press fit connection is going up to 300 amps. RedCube plug is also a press fit connection with an additional plug. And then we have also the RedCube SMT range. When you're just on your first layer of the PCB, you can also use the RedCube SMT range. But on the first layer, you can imagine you cannot transport that much current as on all layers with the press fit technology. So we have a closer look on the press fit technology now. How does it work? Yes, it's a solder-free, it's a gas-tight and a powerful electrical connection. But how does it work? You have a solid pin, and this solid pin gets pressed by force into the via of the PCB, the copper via of the PCB. And then under the tin layer of our product, we do not have a nickel layer like for soldering products. We have a copper layer under the tin layer on our product. And that means you get a cold welding situation. You can see it here in this picture, between the via in the PCB and our component. And this cold welding situation leads to a very low contact resistance, which you can see into the further slides. So let's have a look on the contact resistance. How is it measured? Yes, there's a standard behind. It's the IEC 6512-2-1. And when we look at a regular connector, we always talk about contact resistances between 10 and 30 milliohms. But when we come to press fit technology, we are talking lower than 200 microohms. And this is a big difference when we're talking about power, because every resistance leads to a warming. And when you have a low resistance, you have low warming on your PCB. And this is the goal we want to reach. Here you can see how it is measured over 2 RedCubes and then divided by 2. And that means less contact resistance leads to less temperature rise. That means an ideal connection for high power. So when you look at the right side of the screen, you can see the different types of press fit elements we offer. We have 2-row elements, circumference elements, and full plane elements. When you say it like this, when you have a copper track in your PCB which goes in one direction, the 2-row element is really good choice for you. But if you have the copper all around the element in your PCB, you should better choose a circumference part. And if you need a very high holding force, then a full plane would be interesting, because every pin leads to a big holding force, as we can see later when we talk about the mechanical stuff. On the left side, you can see derating curves for different circumference products. We have one with 12 pins. It goes up to 175 amps. One with 16 pins goes up to 250 amps. And the 20-pin solution goes up to 350 amps. But it also depends on the cable you can apply. If you use a cable, for example, with 95 square millimeters, you can only handle 292 amps and not the 350. So when you want to use the 20-pin connector with 350 amps, you have to use a bigger cable, like 120 square millimeters, for example. All the derating curves end at 150 degrees, but this is related to the FR4 material of our PCB. And the test was done with 4 layers with 105 micrometers per layer PCB with FR4 material standard. Let's have a look at the mechanical performance of the press fit technology. How is this measured? It's measured in a pull-out test. And there we can see we have a big extraction effort. It's around 10 kilogram per pin, or the other way around, 100 Newton per pin. And this is measured with a PCB 1.6 millimeter thick. The thickness of our PCB for the press fit technology can be between 1.6 millimeters and 3.2 millimeters. This is related to the pin length of our products. The pin length is 3.8 millimeters. And to control a proper press fit technology, you have to turn around your PCB and you have to watch if the pin looks out of the PCB. And this leads to the PCB thicknesses between 1.6 and 3.2 millimeters. So I can tell you these are strong products, but I can also prove it. And therefore we made a small test. We just pressed in one full plane RedCube into a 3.2 millimeter PCB, as you can see here on the right side. And this is connected to this angle here. And you see now my colleague, what he's doing with the press fit technology. So you can see this product has really a very good mechanical, a very high mechanical performance. So, but now we come to the solution. How does press fit work? What do we have to do when we want to establish a press fit connection on our PCB? First of all, we need a drill hole. The drill hole has to be 1.6 millimeters with plus tolerances, but without minus tolerances. Why do we not have minus tolerances here? Because the pin should only touch the FR4 material, but not destroy it. That means the pin has a square of 1.6 millimeters. And if we have a hole with 1.6 millimeter, it just touches the hole on the side, as you can see on the left picture. What we have to do next, we have to bring copper into our via. There we can choose between 25 micrometers and 40 micrometers. The optimum is here in between 30 and 40 micrometers, because then we have enough space for our cold welding situation, which will be established during the press fit process. But we need another thing. We have to avoid oxidation, and therefore we need a little thin layer. The tin layer has not to be very thick. So it is possible to do a tin layer up to 15 micrometers, but it doesn't make a big sense. The optimum is only 2 micrometers. We need it only to avoid oxidation before the press fit process starts. And if you have a lot of tin in your application, this leads to a big span during the press fit process, and this is what we want to avoid. So a tin layer of 2 micrometers is totally enough. We have also around between 2 and 4 micrometers on our product itself, so that the press fit process will take place in a smooth way. At the end, diameter of the via has to be 1.475 millimeters for chemical values when you have a chemical surface on your PCB. And this is the result when the pin is pressed into the PCB. You can see here your copper via. It's a little bit deformed, but it's not destroyed. And here, all on these points, we reach the cold welding situation. We will see this later in a bigger picture a little bit better. So how does it work? Here's the picture again. Our goal is to reach a connection angle here between 10 and 15 degrees. And when we look at the connection angle and we have between 10 and 15 degrees, we have a big space for the connection itself. And this space for the connection is bigger than the space of the pin itself. So there is no electrical, let's say, bottleneck in the press fit connection itself. And now you can see the cold welding situation on the right side. And there you can see also the copper in our product. This is the copper layer in our product. And this copper layer gets welded together with the copper layer in the via of the PCB. And this leads to a homogeneous situation here. And this is all really, really gas tight thing. And it's cold welding, which is established between the copper of the via and the copper of our product. And this means there is no gas, no possibility of any gas entrance or any dust entrance in the system. So it's very reliable regarding the environmental situation. So, but how can I design my PCB when I want to transport that power? It's also important that you have enough copper in your PCBs, and there is no really standard for the press fit technology behind. So what we did at Würth Electronics, we developed a kind of rule of thumb for it. But all our customers which work with the press fit technology using this rule of thumb, and it works really in a proper good way. So I will show it to you in the next 2 slides. So what do we have to respect regarding the width of our track? It should be 3 times the width of our product. For example, when we have a product with 7 millimeters, the width of the track should be 21 millimeters. And regarding the thickness, we have to look at the current we want to transport. The current has to be divided by 0.3, and then you get the thickness of the copper for the PCB. And this you can divide again into the layers, and we make a little example on the next slide. So here we have our component with 7 millimeters length, or 7 millimeters, and our track has to be 21 millimeters, 7 multiplied by 3. And the thickness, we want to transport 100 amps, but divided by 0.3 leads to 330 micrometers we want to have in our PCB. And there we can decide if we want to have 4 or 5 layers of 70 micrometers. This is the best solution, as we can see later, because we tested it. Or it's also possible you can use 3 layers with around 105 micrometers of copper inside. 105 micrometers is the maximum copper amount per layer, which is possible to bring into a standard FR4 material. That's the reason for the 105 micrometers. But you can also choose more layers with let's say 4 or 5 with around 70 micrometers. And then you are always on the safe side using this rule of thumb. We did some temperature rise tests, and therefore we established the PCBs. Here we have the 4 layers with 70 micrometers and 21 millimeters wide. And for example, here we have smaller layers, only 10.5 millimeters wide, and there we made some temperature tests regarding the existing temperature. You will see later on another slide. So this is the temperature rise test we did with a working current of the 100 amps you saw before. We have 4 layers chosen with 70 micrometers, and they are 21 millimeter wide. And we have an ambient temperature when we start of 21 degrees. And as you can see here, the warming is only about 45 Kelvin. And the warmest place is in the middle of the PCB and not on the press fit connection. This you can also see when we start the bottom view. Here the bottom view shows you also that the warmest point on this connection is in the middle of the PCB, and perhaps sometimes also on the cable, but not in the press fit connection itself. Because remember, it's got a resistance lower than 200 microohm, and this leads not to a warming on the press fit element zone. So what do we have to remind? The rule of thumb design gives a good temperature balance of the full system, but sure, we recommend to do a small temperature rise tests when you do your prototypes, but the press fit connection does not bring an additional warming because of the low contact resistance. So here you can see the different examples we made. So it's also important to have the right cable adapted. For example, we did the 100 amp test with a 10 square millimeter cable, and we reached a warming of 63 Kelvin, or 64 Kelvin in the PCB, and this is really a lot. But when we do the same with a 16 square millimeter cable, as you can see here, we only have a warming of around 40 Kelvin. We have 45 Kelvin at the press fit zone itself and 48 Kelvin in the middle of the PCB. A really good result. This we can use in our application for a long time in a proper way. And when we do smaller layers like this one, 10.5 millimeters, we get a much higher warming, around 98 Kelvin. So it's not a good idea to do this. So you should always have the width of the track three times the width of the product itself. Then you are on the safe side, as you can see here. And also, please respect the cable. The cable can also pull out the heat of the whole system. That means the bigger the cable is you use, the better is the heat transportation out of your PCB into the environment. And this is a good idea, and you reach good values for your application. So let's bring it together. RedCube is small, is established high currents, is cooling down PCBs. And the rule of thumb is high current design is a good approach, but please check the temperature with a prototype test for the first time, and then you are sure for your application when it goes into series. Okay, press fit process. What do we need for a press fit process? Okay, of course, we need a press to do the press fit process. Makes sense. But also we need the PCB, we need a support. The support is very important. You have to support every hole of the PCB. Otherwise, there's a risk to crack the PCB or to crack components on the PCB. You need also a stamp depends on the press fit element you want to use, and also a base on your press. And then when we come to the specification of your via, and you have a chemical surface like chemical tin or ENIC, that means nickel and gold, then we have an end diameter of 1.475 millimeters with 500th millimeters of tolerances. And meanwhile, every PCB manufacturer is able to do this and to prepare your PCBs in this way. But please mark it a little bit, like this is the press fit zone, so that your PCB manufacturer knows that the tolerances have to be very tight. When we do not have a chemical surface, we can also have a hull surface, for example. hot air leveling. But when you have a whole surface in your PCB, it's not always the same thickness at the same point, as you can see here. There can be some bigger spaces filled with tin or some smaller spaces with tin. And this leads to a lower end diameter we need, but therefore we need a diameter of 1.45 millimeters, also with 500 tolerances behind. And now you can decide which is your surface of your PCB. Is a chemical surface, then it's 1.475, and if it's a hole surface, you have to use the 1.45 drill hole. But both specifications you can find on the data sheets of our press fit components. When you want to do the press fit into a pure copper bar instead of a PCB, what is also possible and also good for transporting higher currents than 300 amps, then you have to respect also the 1.45 millimeters. Why is it like this? Because the copper bar drills are not so precise as the drills in the PCB. And most times they are done by a metal drill and not by a laser. And that means the tolerances have to be a little bit bigger. And so we take the 1.45 millimeters as the diameter so that you are on your safe side with your application. Another hint, which is important, you should stay with small SMT components at least 4 millimeters away from the press fit zone. Why? Because you bring a lot of pressure on the press fit zone, and the press fit is the last thing you do after you have soldered all your components on your PCB. The last step is the press fit step. And then all the components are already on the PCB. And when they are too close on the press fit zone, the pressure you bring on the PCB can make some cracks in small SMT components. And this we want to avoid. Therefore, you have to stay away about 4 millimeters with small SMT components, especially MLCC caps, for example, or small resistors. They can easily become a crack inside, and this we have to avoid. So stay away with them at least 4 millimeters. If you have the possibility to stay away from the edge of the PCB, you should use a distance of 3 millimeters, especially for small PCBs like 1.6 millimeters, not to destroy the PCB during the press fit process. And as I already said, the thickness of our PCB can be between 1.6 and 3.2 millimeters. And there we could show you how the press fit works. It's no rocket engineering. It's quite easy. You can see a small video. One moment, please. So that's it. Now the control is coming. Just turning around the PCB and watch if the pins are looking out, then the press fit process is done in a good way. But you can see it was done with a proper support. This support in this case was done out of a 3D printer. But we have a closer look on the support later. Now. We need a support location. For prototyping, you could do a 3D printing. Therefore, you can also receive some 3D files from our side if you want to have it. And then you can do support by 3D printing, and it lasts for the prototypes for, let's say, around 100 press fit processes. But then the material gets a little bit weak, and you have to choose another material for the series. So, but the most important thing of the location, the holes have to be 1.75 millimeters, because then the pin is going into the hole without touching anything and is supporting your PCB in the best way. This is a support location made for a special PCB. It's a metal finished version. And there are also some companies we can recommend to you for the support location if you want. Therefore, just write me an email, please, and I can send you some companies which are able to do the support location for your PCB. Because every PCB looks a little bit different, yeah, and that means you can have also SMT components on the downside of the PCB, and then you need some carvings in the support to not to destroy those elements on your PCB. That means every support location is for every PCB a little bit different. But therefore, we can recommend you some companies which are able to do that. So I've got another example for you. It's also important to fix the PCB on the support locating so that it cannot move during the press fit process. This is, for example, possible with a small frame like that here, or with some needles where you put the PCB on and also put the support on, and then you are sure that nothing can move during the press fit process. So here we have a real case support of a PCB with also components on the bottom side. And there you can see for the press fit, we have here the big zones, but everything else is not supported. And this is also important because we have components, SMT components, as you can see here, which have to be protected. And below and beside of the components are the press fit elements, and the press fit are perfect supported with this zone. And this you can do for your application. It depends on your application how it looks like. The next important thing is to use the right stamp. The base material of our components is brass, and brass is not steel. That means it's not very, very weak. It's a very soft material. And when you just use a standard press and press, for example, on the top of the thread here, you can destroy the thread. That means after that, you cannot insert any screw anymore. And therefore, you need a special stamp, which is pressing here and not on the top of the thread. This is really important, depends also which component you want to use. You need the fitting stamp for the fitting component. We also have two-part elements that you can press into the PCB. There it is important to press in first the ground element and then the support element. Also a small video for that for you. So now the support element is coming. Gets pressed from the bottom side and is fixed together on the whole PCB. The press fit process is done. Perfect. If you have a component like this, you have to use another stamp, for example, which presses on 2 points. So this is very important that the product gets really straight into your PCB and does not move in any angle during the press fit process. Yeah, for the press, we can recommend you 2 companies in Germany, Schmidt and Gächter presses. So we are using Schmidt presses also in our company, and this is what we can recommend. But we can also recommend some companies for the support location. Therefore, please write me just an email. So, but when I want to choose a press, I have to take care about the press dimension because we have big insertion forces. And those are the insertion forces we have. For example, regarding the thicknesses of PCBs, okay, if we have 3.2 millimeters, the highest forces are there. And we do a little example with a chemical tin surface and a 3.2 millimeter thick PCB. And we have a RedCube with 12 pins, for example. Then we have to multiply 12 by 14. And then we have this 1.7 kilonewton. And the press should be in between 1.7 kilonewton and 4 kilonewton. This is 340 multiplied by 12. So this is the range the press should work in a proper way. And you should also use a little bit of security margin. That means we always use 20% security margin. If you have 12 RedCube pins, the press effort should be around 4 kilonewton, we said. And therefore, we buy a press with 5 kilonewton, and then you are sure always on the safe side. And when you use a mechanical press, it's not necessary to do a thing here when you move it by hand. But if you use a hydraulic or pneumatic press, you have to take care about a little bit distance to the PCB because of the tolerances. When you do it by hand, you can feel the tolerances, but when you do it mechanically or automatically, the press doesn't take care for the tolerances and destroys the PCB if there is no gap of 0.1 millimeters. And the flat zone of our pin should exceed the PCB to be sure that every layer of the PCB is contacted with our zone. Insertion speed should be around 100 and 250 millimeters per minute, and it should be done in one single time, the press fit process. Not doing it more times, just one single time. And this is the tools we offer also for our terminals. Therefore, we have a big plier for the cable lugs to press them on the cable in the proper way, and also for the plugs for the RedCube plug. Okay, but what if it's not possible for you to do a press fit process? Then you can use our THR components. Therefore, sure, you need a bigger hole in your PCB because they have to be placed by machine automatically, so they have to fall into the via, and the via has to be 1.85 millimeters in this case. But the difference, I said it in the beginning also, with the press fit technology, you can reach up to 350 amps, but with the THR, you have solar material in between. That means you can only reach around 85 amps because of the higher contact resistance. When you use the THR component, we also offer our stencil suggestion. This is important for you because you need a little bigger holes on the stencil, as you can see here, 3.1 millimeters. Then the hole itself, has 1.8 millimeters because of the material which has to be squeegeed into the via before the component is placed. So this is how the THR process works. You position your stencil on your PCB, then you go over it with a squeegee, and as you can see here, a little bit of the material is just pressed into the via. And then you take your component, put it into the PCB, and then it gets soldered in the reflow oven, and at the end the component is soldered in a proper way. And there is also an IPC rule for it. It has to be filled at least with 75%. And those are solder examples you can see. On the left side, 100% filled solder result, and acceptable soldering with 75% filled. This also leads, because of the bubbles you can have in the soldering, this reduces the 100% to the 75% in most cases. We have also SMT components, but be aware they are only suitable for current on the first layer of your PCB. There we have three different types: an open thread type, one to increase the torque. If you need a high torque, you can use the flat one, or if you need a centering on the PCB with a center pin. But what is important for the SMT components, a non-plated through hole. We always recommend the non-plated through hole because there are some problems when you have a plated through holes. As you can see here, the tin goes into the through hole, and this is into the thread also. And this is really hard to put a screw into the thread when tin is inside. So this will not work in a proper way, as you can see here. And also the product gets disaligned when you put it in the reflow oven. Why? When you put the product in the reflow oven, it gets first warm from one side, and from this side the heat is coming, the product is moving, and the product is not centered anymore, as you can see here. And when you have two big PCBs and you want to bring them together with this component, it can lead to some trouble because it's not centered anymore. So please do not plate the through hole. So, and another reason, therefore, some customers said in the past, but when I do a plating in the through, it should have a higher shear force, but it doesn't. The shear force for a non-plated through hole is between 490 to 590 Newton, and a plated through hole is between 280 and 440 Newton, a lower force. So a non-plated through hole is recommended from our side. At the end, I want to show you some applications with press fit technology. For example, a copper bar, or we do have also press fit technology in the Formula E for the motor steering, for the motor control. And we are for example, a particular board-to-board connection, or here a high power backplane with a lot of press fit elements on it. For battery applications, of high power batteries are also very good to use press fit components because of the low resistance. And we can have a double side mounting. We can have an IGBT connection. An IGBT switch is always high current, so this is also a good solution for that. And also for laminated fuses, which go higher than 50 amps. This one is for 80 amps, for example. Can be used in a truck, a lorry, or any farming machine. And also for high current board-to-board applications. This is a welding machine, and this customer has 200 amps from the lower PCB to the upper PCB with a board-to-board connection and also a strong mechanical connection with the RedCubes. This is a copper bar distribution. There, the current is carried around the copper bar to different RedCube plugs. And at the end, I will show you something which does a friend of mine. He is transforming ultralight microlight planes into electric microlight planes. And therefore, he needs a power of 85 kilowatts. And this is done with 17 RedCubes, which are placed on the PCB, on the motor control PCB, you can see here, and also on the battery side of the PCB. So this should it be with my presentation. And now I'm really interested in your questions. Thanks for joining the webinar.
So then, thank you, Stephan, for your presentation. And yeah, as you already said, now we would go into the questions. So yeah, we will just start right in. One information, because I see there are already some questions in. If we can't have the time or can't answer your question now in the live webinar, we will answer them later on. And also just the information, you will also get the link to the presentation as well as to the recording from us in the next few days by mail. So, Stephan, let's start. First question. How can the press fit connection temperature be lower as the trace itself, even if the press fit resistance is in a microampere range? It is still higher than the copper trace itself.
Yes, this is related to the geometry of the PCB, because the copper in the PCB is not open and has no possibility to do a convection with the air. It's inside of the PCB, especially in the inner layers, and that means that the PCB itself gets a little bit hotter than the press fit component. The press fit component can be cooled by air, and also the cable is pulling out the heat of the press fit component, but this is not possible in the middle of the trace of the PCB. So the middle of the trace at the PCB is the most warm, the warmest place on the application in most cases.
Okay, Stephan, thank you very much. Then
Welcome.
Next question here. For RedCube plug, what is the extraction force to unplug when it is in lock condition? Is there any test done before?
Yes, we did tests for that, and there you need a force higher than 5 kilograms. Higher than, if you pull on the RedCube plug with higher than 5 kilograms, it releases and comes out of the system. But the system is not destroyed. Afterwards you can use it again by pressing it again and putting it inside. Normally you should not do that, because you will leave some scratches on the plug itself. Because this is a low, let's say a zero force insertion. When you press the component, you need no force to put it in, and this leads to a better, you can protect the surface of the component better in this way than pulling it on the rough way, on the hard way. But 5 kilograms is the value.
Okay, thank you very much. Then from the same attendee, also the following question. Any reliability test report available for the RedCube plug MPN 7464-100?
Yes, there are several reliability reports available. Yes, this is the part number. There are several reliability reports available for press fit technology and also for the plug. I can send it to you. Just give me your email address, and I can send you the reliability report for it. And if you have any questions left, we can discuss this by telephone or by email anyway.
Perfect. Then thank you very much. Then we will come to the next question. Can I also use the press fit elements in an aluminum bar? Do you have specifications for that?
Okay, in general, I think it would be possible to use it in an aluminum bar, but we have no really examples for it, and we did not really test it, to be honest. We tested it in a copper bar. In a copper bar, it works in a good way. But the problem with the aluminium may be that the aluminium is has a different strength, and the press fit process itself would not go as soft as it goes into copper. So we have to check this. Regarding the resistance, we would get a good result, I think, because aluminium is also a good material to transport electricity. But we have to take care for the press fit process itself, and we are going to do some tests in the future because we have this question already before, and therefore I can give you an answer in around a quarter of a year.
Okay, thank you very much, Stephan.
Welcome.
Next question regarding environmental influences. Which is the most safe connection, THR, SMT, or press fit?
This is easy to give an answer. This is absolutely press fit connection because of the cold welding. The cold welding is a gas tight connection. You will never reach a gas tight connection with the other solutions. So that means, and you also have a welding situation between copper and copper. And those materials are the same materials, and this leads to the lowest contact resistance and also to a gas tight connection, which is very reliable regarding environmental situations. This is also the reason why the colleague is using it for airplanes. So if it would not be reliable, it would not be a good idea to put it in an airplane. So this is really the most reliable connection is the press fit connection.
Yeah, that's good to hear. Okay, the next question. Is there a RedCube plug available higher rated than 120 amps?
Unfortunately not. This is because of the geometry of the plug itself. Up until now, we were not able to develop a plug which can take a thicker cable than 16 square millimeters. And the 120 amps are related to the cable with 16 square millimeters. And therefore, you would need 25 square millimeters, and this is too big and leads to a too heavy cable. And when you have a too heavy cable into the RedCube plug, you have to take care about the contact zone because you bend it a little bit, and then you have a smaller contact zone, and the resistance is going up. So that's the reason why we have it only up for a 16 square millimeters cable, or let's say the other way around for 120 amps.
Okay. Yeah. So then, yeah, I see two more questions at the moment. We have still some time left, of course. Maybe you want to go to lunch, but this time we will take.
Okay.
How can I
No
transport current over the inner layers when using an SMT RedCube?
This is also possible, but then you have to take care for some vias. And please do not place the vias under the component, but close to the component. You have to place the vias around the component, close to the component. As much vias you need for your current depends on the amount of current you want to transport over your layers, but you have to do it with vias. It's close to the SMT component itself.
Okay. Then last question for now. Can I use your press fit elements for thicker PCBs than 3.2 millimeters?
In general, let's say it's possible, but there you need a special component from our side. So then we need a component which is a little bit longer than 3.8 millimeters. We also established components with 4 millimeters, suitable for PCBs around 4 millimeter. And this is also possible, but then longer than 4 millimeter is a little bit tricky because then you have the danger to bend the pin during the press fit process when it is too long. So we can establish it up to 4 millimeters on special release for a customer if he needs for a 4 millimeter PCB, but thicker than 4 millimeters, I would not recommend.
Okay, thank you very much. So
you're welcome.
One last question I see here, then it's also time for the end of the webinar, but yeah. Stephan, do you support CAD footprints for PCB software for both with and without press machine?
I did not get the question in the right way. Can you repeat it again?
Yeah. Do you support CAD footprints for PCB software? That's the main.
Yes, we support CAD footprints for the PCB softwares directly at the components on our website. When you go to the component on our website, you can see a download section where you can download the CAD files for your application. Like we offer it for incl, we offer it for Altium, for example, but we also offer the standard CAD file for standard software.
Okay, exactly. So if you have any questions left now, or you can't find the download section, then just email us, maybe at digital-v-days@we-online.com. So then I would say thank you very much for your attention. Stephan, thank you for your presentation and all the answers.
Welcome. Thanks for joining.
Have a good day, enjoy lunch, and yeah, stay tuned with our Digital V Days. Goodbye.
Thank you, bye.